I am Roberta Pirazzini from the Finnish Meteorological Institute in Helsinki, and I'm going to present drone-based sea ice albedo measurements during the mosaic expedition at the time of the Arctic freeze-up. My colleague Henaretta Annula, also from the Finnish Meteorological Institute, and Ruji Dadadi from Victoria University of Wellington, New Zealand, have also contributed to this material. What is the background of our study? Arctic air temperature is increasing at more than twice the global rate, which is a phenomenon referred to as Arctic amplification. Reduced summer albedo caused by sea ice retreat and surface melting is one of the major causes of Arctic amplification. And the darkening of the Arctic Ocean surface resulting from the decrease of albedo causes an increase in the absorption of sunlight by the Arctic Ocean during the warm season, which further contribute to the sea ice melting. This positive feedback is called ice albedo feedback. Melt pond contribute to ice albedo feedback because they reduce the albedo. But the problem is that the ice albedo feedback is still poorly represented in model. And so to understand the role of sea ice albedo in the climate change and realistically model it, we need to understand the processes that control the sea ice albedo. The research questions that we wanted to answer with the measurements I'm presenting here are: what is the evolution of surface albedo at different horizontal scales, from the few meter footprint of surface-based measurements up to 100-meter footprint of satellite observations? And what is the role of various surface features, melt pond, ridges, leads, on the aerial averaged albedo during the freeze-up period? And what is the surface roughness defined at different horizontal scales, from millimeter to 100 meters, and its roles on albedo? So basically, we want to address processes that changes a different horizontal scale and that affect the albedo. The observations that I am presenting here were collected during mosaic leg 5, which is the last leg of the expedition, from August to September 2020. Before leg 5, the research vessel Polarstern drifted attached to an ice floe for about 10 months, following this red track here, with few breaks. But then this floe disintegrated when it reached the Fram Strait in July 2020. And so in our leg, we went to close to the North Pole to search for another floe. And the leg 5 track is circled in yellow here. Despite the discontinuity of the measurement area, we consider the observation in both ice floe representative of the surrounding Arctic. And the peculiarity of the observation we carried out in leg 5 is that we capture the transition from the melting to the freezing ice. This drawing describes the multitude of activities that were carried out in the ice floe. It was truly a multidisciplinary observatory. In these yellow circles, I marked the two figures, me and my colleague, that were making in the upper one drone measurements. Here is the drone, and in the lower one snow measurements. The simultaneous observations of hundreds of physical and biological variables will enable the studies of those processes that cross different disciplines and also different horizontal scales, as there were here, as you see, fixed measurements, transects, airborne measurements, and also underwater measurements. The datasets that I'm going to present in this presentation are drone-based albedo observations, drone-based digital elevation models obtained from photogrammetry, broadband albedo and radiation data from the fixed FMI radiation station, and snow surface scattering layer observation, focusing on microstructure and mini digital elevation model from structure from motion. How did we measure the albedo? Here the figure on the right illustrates the instrument that we used in Mosaic. On the top is the fixed station measuring all the components of the surface radiation budget, that is the broadband, unwelling and upwelling thermal and solar radiation. Enlarged on the right are the two pyranometers measuring the solar irradiance. The glass of the downward-looking sensor is hardly visible, but is there. And the albedo is calculated from this equation, that is from the ratio between the reflected and incident solar irradiance. We also had a drone in the lower figure to measure the incident and reflected broadband and spectral irradiance, from which we calculated the spectral and broadband albedo. While the broadband albedo refers to the whole solar spectrum between 300 and 3000 nanometer, the spectral albedo was measured only in the 350-1100 nanometer wavelength range, corresponding to visible and near-infrared radiation. These photo-mosaics show the evolution of the surface condition experienced in Mosaic Leg 5, from the initial melting with all melt pond clearly visible and still enlarging, to the freezing and the beginning of snow accumulation. The polar stern vessel is visible at the bottom of each photo-mosaic. On the 6th of September, here, we see that few melt ponds are no more visible, meaning that the surface has frozen and they have been covered by a thin layer of snow. On 8th of September, also some leads have frozen, but most melt ponds are still well visible, although their surface is frozen. When the new ice thickens on 10th of September, most melt ponds disappear, to reappear for a while a few days later after a rain event. This evolution of the surface albedo is well captured by the time series of albedo measurements at the fixed FMI radiation station. These four photos here clearly show the changes from the melting condition to the freezing, and then again the reappearance of the melt pond after the rain, and the new snow deposition at the end of the observing period. In Leg 5, the pyranometers were placed right above a melt pond. The field of view of the downward-looking pyranometer is a radius of approximately 3 meters from the vertical of the sensor. Hence, also the white scattering ice contributes to the measured reflected irradiance. These are raw data, not yet cleaned from the spikes due to frost in the dome of the sensors. Anyhow, what we can see here that the initial albedo was around 0.35, and then during freezing it rose quickly to over 0.5. It dropped to 0.7 after the rainy event and rose again above 0.8 at the end of the expedition. Our fixed radiation station was installed on the ice floe at the beginning of the Mosaic campaign. So to place the albedo measurements that we did in Leg 5 into the perspective of the whole spring and summer measurements, we look here at the albedo time series from mid-March to mid-September 2020. Before the start of the melt, the surface albedo kept oscillating between 0.8 and 0.9. But the start of the melting occurred in late May or June, and unfortunately it was not recorded because the ice floe had to be temporarily abandoned to exchange personnel and get supply. In July, when the field was re-established, the field measurements were re-established, melt ponds were already well developed, and the albedo of 0.6 here measured by the station reflects the position of the downward looking sensor with respect to the nearby ponds. The minimum albedo is measured at the beginning of leg 5 when the downward looking sensor is positioned just above a melt pond here. A fixed station that we have seen provide a nice time series, but it represents only the type of surface that it is located below it. To have a better understanding of the spatial heterogeneity of albedo and measure the area average albedo that correspond to the satellite footprint, that is 100-300 meters in the case of sentinel sensors, we need aerial measurements from the drone. However, the possibility to fly was limited by the weather condition. Often there was too high wind or fog or precipitation, by the sky occasionally reserved for helicopter operations or balloons, and by the schedule of the field work and by the battery power. We managed altogether to perform 17 flights corresponding to about 5 flight hours, measuring albedo along horizontal transects up 5, 10 and 30 meters above the sea level, and also along vertical profile over selected target points. The main challenges for the flights were that we could not trust the compass, and therefore we needed to do manual landing and takeoff because we were too close to the North Pole. Also, the cold and moist air often caused the formation of ice on the blade of the drones. And we were at the end of the summer, so the solar zenith angle was very high, and the little amount of solar radiation caused a high noise in the data. With a smaller drone, the Mavic 2 Pro, we took photos of the area where we flew with a Spectra drone. We applied a serpentine pattern to reach a high overlap of consecutive photos. In this way, we could reconstruct photo-mosaic maps of the surface and even calculate digital elevation model of the surface applying photogrammetry. We obtained 25 maps corresponding to approximately 11.5 flight hours. In the photo on the right, we can well see the ice formed on the blades during one flight. This is extremely dangerous. When it happens, the drone starts descending and it may be problematic to control it. The flight patterns of our Mavic drone are marked in yellow, while those of Spectra drone are marked in red. Crosses here mark the starting point of the flights, and the red dots mark the location where we took repeated vertical profile of albedo, flying the drone from surface up to 30-50 meters. Here we take a first look into the broadband albedo measured with the Spectra drone. The upper plot is taken on 1st of September and the lower plot on 4th of September. We see that the aerial averaged albedo measured on a 5 meter and 10 meter elevation, that is marked in blue, have higher variability than the aerial averaged albedo measured at the elevation of 30 meters, that is marked in red. This is because the 30 meter albedo is not significantly affected by the individual surface features, and therefore it is potentially representative for satellite footprint and model grid area. Surface-based albedo observations were made on fixed, continuously measuring stations and along repeated transects using portable instruments, as along the albedo Kinder line here in the photos, highlighted with a red line. These observations have a footprint of few square meters, and therefore they represent only the albedo of the surface features right below the sensors. But to check if the albedo averaged along the Kinder line represent also the averaged albedo over a wider area or not, we compared it with the drone-based albedo measured at the height of 30 meters. On the 1st and 4th of December, both the averaged ground-based albedo and the drone-based albedo were around 0.4, while on 11th of December, when the sun was visible through a thin stratus cloud generating shadows at the surface, the drone-based albedo was slightly lower than the averaged albedo along the Kinder line. This tells us about the impact of the surface roughness when the illumination is not completely diffuse, and you can see the shadows in the photo-mosaics here below. Here. The photos taken with the Mavic drone are used to produce photo-mosaics, maps, and digital elevation models of the surface. Here on the left are examples of photo-mosaic maps, and on their right the first attempt to make digital elevation models of the surface, applying photogrammetry techniques. In these initial products, ground checkpoints have not yet been applied, and they would enable the removal of the surface tilt that is clearly visible in these images. The yellow star in the photo-mosaic map marks our drone's takeoff station, while the red star marks the location of a sea ice mass balance buoy above which we took a vertical profile of albedo. What do we get from photo-mosaics and digital elevation models? Well, we will use the photo-mosaic maps to extract fractional area of melt ponds, light blue and dark blue one, which are associated to different ice type, and also the fractional area of ridges and leads. In addition, the albedo measured by the spectra drone can be used to calibrate the photo-mosaic maps and extract the albedo of the single surface feature in the map, like melt ponds, ridges, and scattering ice. We saw that surface roughness affects the albedo. To understand how much and when, we need to measure the roughness, and that is possible through the digital elevation models that can provide heights of surface point with respect to the sea level at a resolution of centimeters. Digital elevation models will be combined with those obtained taking manual photos of a small surface area, less than 1 square meter, surrounded by targets, as in this photo. Applying structure from motion image processing technique, we can get this small scale digital elevation model which have sub-millimeter resolution. Combining this with the large-scale drone-based digital elevation models, we get the surface roughness at various scales, which is very useful because different scale of roughness impact different processes. The reflection and absorption of solar radiation is affected by the sub-millimeter and millimeter scales, while microwave signals by the centimeter scale, and the near-surface airflow is affected by the decimeter and meter roughness scales. Let's now go a bit deeper into the interaction of the solar radiation with the snow and ice. First of all, which kind of ice surface do we observe during the summer? In the photo on the right, you can see some white stuff covering the area next to the melt pond. This is not snow, it is the so-called surface scattering layer. During the sunlight season, sea ice surface absorbs a significant fraction of the incident solar radiation. This energy causes melting and metamorphism, which result in the formation of an intricate structure of fragile ice crystals permeated by void spaces called surface scattering layer. This structure continues melting and reforming, eroding the underlying ice until the end of the summer, when the freeze-up begins. Because of this structure, typical of porous media, the ice scattering layer exhibits much larger scattering than the ice underneath it. In radiative transfer models, porous media such as snow and surface scattering layer are represented as a collection of spheres or other polyhedrons, and their scattering property depend on their effective radius. As shown in this plot of modeled snow spectral albedo as a function of wavelength for different snow effective grain sizes, smaller is the grain size and larger is the albedo, especially in the near-infrared wavelength. Here we used grain size and effective radius independently, they are the same thing. The effective radius is the inverse of the specific surface area, which is more often used in field measurements, and I will use this specific surface area from now on. And because of this strong relationship between SSA, the specific surface area, and albedo, the albedo can be modeled from the knowledge of the near surface SSA, and vice versa, SSA can be derived from the spectral albedo measurements. Here on the right, we see a microcomputer tomography scan of the uppermost 5 cm of the surface taken by my colleague Roberta during the last leg of Mosaic. From this scan, we get the most precise measurement of SSA. On that day, we see that there was snow covering the sea ice. Visually, we could not really understand the difference, but from this scan, we clearly see that the sea ice crystals are larger than the snow crystal, and therefore they have a lower albedo. As I said, X-ray microcomputer tomography provides the most accurate measurement of SSA. For the first time, there was a cold lab in the ship, a container that was kept at -20 degrees Celsius, where snow and ice samples were analyzed right after their collection from the field. These 3 images here illustrate the surface evolution toward the end of the campaign, when large surface hoar crystal formed at the surface. Near-infrared images were another method applied in Mosaic to derive the specific surface area of snow and ice scattering layer. Optical methods like these rely on empirical correlation or a radiative transfer modeling to establish the correspondence between the measured snow reflectance and the snow-specific surface area. The box covered by a black curtain in the photos on the left contains the camera and can be placed at the surface or in a snow pit, facing the wall of a snow and ice scattering layer. On the right, we see how a snow and ice vertical wall looks like in a near-infrared photo. We can see all the different layers, and the different shades of gray correspond to different SSA. In this nice photo, you see Roberta with a snow micropen, which is a high-resolution penetrometer that measures the resistive force produced when a rod penetrates perpendicularly into the snow and ice scattering layer. With this instrument, we get the vertical profile of densities, specific surface area, and thermal conductivity through empirical relationship with the measured resistive force. And with this, I finish my presentation. I hope I have made you curious to know more about the Mosaic experiment and the many measurements that were collected. I invite you to read more about the Mosaic observation in these 3 papers that provide overviews on the sea ice, atmosphere, and physical oceanography measurements. Thank you and bye.